Welcome under another roof, where there is always another proof. They call me the Witch of Agnesi. Don't stare like that. I'm not crazy. But I am no ordinary magician, just a humble mathematician, and with your permission, in this edition, a proposition regarding a simple addition. What concoction shall I brew? Come closer, I'll share a clue. Of all my recipes, this one shines, for this mixture surely defines a most irrational solution, despite its rational constitution. To uncover the secrets within with some odd numbers is how we begin. 1, 3, 5, 7, 9, etc. They're reciprocals, this brew's progenitor. Including them all would be an error, adding every second is far more clever. For now we remove those left out, and what remains there can be no doubt. This glorious formula, I cannot lie, yields exactly a quarter of pi. A question burns, I hear you cry, keep watching to explore. Why? So, the Leibniz Formula for pi. Somehow, if you take the alternating sum of the reciprocals of odd numbers, pi. Where there is pi, there is a circle. But what do these reciprocals of odd numbers have to do with circles? Allow me to show you a curve that stems from a circle which, on one hand, will produce pi, and on the other hand, will produce these reciprocals of odd numbers. This curve has a special name. The Witch. Seriously, that's what we call it, the Witch of Agnesi. And there's a fun story behind that name that led me into the deepest research rabbit hole I've ever tumbled into, and we'll get into that later. No Halloween video would be complete without some horrifying mathematics. We'll soon be looking at a bit of Euclidean geometry, convergent geometric series, and calculus. But don't let that scare you. I'll explain everything, so if you have knowledge gaps in those areas, you'll still be able to follow along. If you're still uncertain about anything we've covered, don't worry, you're not alone. I receive a lot of emails from viewers saying that they never got a chance to study mathematics at a higher level. So what's the best way to learn now? Luckily, there's an answer, and that's this video's sponsor, Brilliant, by providing a free and easy to use platform. Whatever your current level, Brilliant has courses for you. Later on, we'll be looking at some Euclidean geometry, and I was shocked to find a goldmine of interactive courses teaching everything from the fundamentals to advanced results. I love how everything is clearly presented, and these hands-on modules are key to developing a strong intuition. All of their courses are delivered in fun, bite-sized chunks, motivating you to learn a little bit each day, with Brilliant customizing your learning experience so that you can learn at your own pace. My degrees were in mathematics, so personally I'm eager to dive in and learn some computer science, but whatever your learning ambitions, Brilliant is the best way to learn. Try everything Brilliant offers today at brilliant.org/anotherroof. Your first 30 days are absolutely free, and the first 200 people to sign up with my link get 20% off their annual premium subscription. That's brilliant.org/anotherroof, or click the link below. Huge thank you to Brilliant for supporting the channel, and now back to the video. So what the heck is this witch curve? To show you, we must first journey to a different plane of reality, the plane dominated by your former partner and life's most fundamental questions. That's right, the X and the Y. I'm speaking, of course, of the Cartesian plane. We will draw a circle such that the x-axis is tangent to the circle and its center is somewhere on the positive y-axis. We'll also draw another tangent to the circle parallel to the x-axis. I'll call this line the ceiling, since all the action is going to take place in this band. Now we draw a ray from the origin through the circle until it hits the ceiling, and I'll call this L. Now here's where the witch comes from. We plot the magic point with y coordinate equal to where L hits the circle and x coordinate to where L meets the ceiling. In effect, we're projecting lines down and across, and where they meet is our magic point. Now let's pick another ray and follow the same steps to plot another magic point, and again, and again, and again, doing the same thing on the other side, and as our ray varies, we trait out a curve that looks like a broad hump. This looks kind of familiar. It looks a lot like the normal distribution, but it isn't. This curve is the witch. Now the witch pops up in all sorts of places. A scaled version of it depicts the Cauchy distribution in probability theory, and it approximates a soliton, a solitary wave. For us, it can shed some insight into this alternating sum. For us, it's the area beneath the witch that hides a lot of surprising mathematics, so that's what we'll want to calculate. First, let's derive a formula for the curve. Now, so far, I haven't actually stated the radius of this circle here. You can make this whatever you want, so really there isn't a single witch, but a whole bunch of witches. Or whatever the collective noun is. A gaggle of witches? We could leave the radius as r and derive a general formula for a general witch, and everything I talk about for the rest of the video does hold in general, but to make the algebra smoother, I'm just going to proceed with the diameter 1 case, so r equals a half. So let's pick a general point on the witch and call it x0, y0. What we want is y0 in terms of x0. That's what a formula is, it's a relationship between the coordinates. So let's think about how this point came to be. Extending upwards and across, we can recover the ray that spawned the point. Pause here if you want to work it out, because it's a fun problem and it doesn't involve anything beyond school level maths. Now there are a few different ways to proceed, but today we'll do it like this. Let's look at this point. It has some x coordinate, say v, and it has y coordinate, y0. And now we'll observe two relationships that link x0 and y0. The first is that this point here, vy0, lies on the circle, so it has to satisfy the circle equation. Generally, circles of radius r centered at AB have this equation. Our circle has center 0, half with radius half, so our circle has this equation. Substituting x equals v and y equals y0, we derive this. So that's something, but we also know something else. This triangle down here is similar to this triangle here, because all of their angles are the same. That means that the ratios of their sides are equal. Now we don't care about v, so we'll make v the subject of both of these relationships, and then we can equate them. And I'm actually going to make v squared the subject of each, because squaring this one is easier than rooting this one. Usually avoiding roots is a good idea. So both of these expressions are equal to v squared, so we can equate them. Now we'll expand this bracket, the quarters die, and now because y0 is strictly greater than 0, we can divide through by y0. And now we just collect the y0s, factor out, divide, and boom. And because this holds regardless of the choice of coordinate, we can just write this as a general formula. Y equals 1 over 1 plus x squared. So that's the formula for the witch in the r equals a half case. If you did it for the general case of radius r, you'll get a formula that looks like this. And you can see now why I chose r equals a half, because it's a heck of a lot simpler. Now that we have a formula, we can calculate and explore the area under the witch. This has a super satisfying answer that's fundamentally tied to this circle here. Before we do, however, we're going to need a couple of lemmas, stepping stone results, related to this expression up here. We essentially want two different ways to write this down. One will yield the alternating sum of the odd reciprocals, and the other will yield pi. So let's do that. First, let's talk about geometric series. Take a look at these sequences. What do they all have in common? They all have a rule where you pick a number and that's what you multiply by each time to get from term to term. That number can be greater than 1, giving an increasing sequence, less than 1, giving a decreasing sequence, or negative, giving an alternating sequence. These are called geometric sequences, and in general, imagine we have a sequence that starts from 1 and we multiply by some number r each time. This will give us a sequence that looks like 1, r, r squared, r cubed, and so on. What if we keep going and stop at the term r to the power of n and then add them all together, thereby forming a geometric series? What does this equal? There is a formula for this, and again there are many ways to derive it, but my favourite is to consider what happens when we multiply the whole thing by 1 minus r. After expanding, we can see that every power of r is going to die apart from r to the n plus 1 on the end. So we're left with r subtract r to the n plus 1, and after dividing by 1 minus r, we obtain an expression for this sum here. But now here's some magic. What if, instead of stopping at r to the power of n, we just keep adding terms forever? In other words, if we let n approach infinity. Well then, so long as r is less than 1, this r to the power of n plus 1 will approach 0 as n approaches infinity. And thus we obtain a well-known formula for the infinite sum of a geometric series. For example, take this famous 1 plus a half plus a quarter plus an eighth and so on. We can get a visual intuition for this by taking a unit square of area 1, adding a rectangle of area half, then area quarter, then area eighth, and so on, and we can see that if we keep going forever, we converge on a total area of 2. And we can verify this with our formula. In this case, r equals a half, so substituting r equals a half into here, we get an answer of 2, as we expect. So this is cool and everything, but you're probably wondering, who cares? Well, this formula here bears a little bit of resemblance to the witch formula. can we marry these together? Well, sure, these two things say the same thing as long as r is equal to negative x squared. So this is the formula for an infinite geometric series where r is equal to negative x squared. What does that sequence look like? Well, we multiply by negative x squared each time. So that's 1 subtract x squared plus x to the 4th, take x to the 6th, and so on. In other words, for a given x coordinate, calculating this infinite series is an alternative way of generating the y-coordinate of the witch. Note, however, that this doesn't necessarily converge, but we'll see later that we don't really need to worry about that. The punchline, though, is that this is an alternating series, which we know is what we're looking for. Put a pin in that, because now we're going to look at something totally different, and that involves a bit of calculus. All we want to do is to differentiate y equals arctan of x. Why do we want to differentiate this? Don't question the witch. You'll see why very soon. Now, this is a pretty standard result that I'm sure many of you know already, and it can be accomplished with school-level calculus. Again, lots of ways to do this, but parental advisory, there is implicit content here. We have x is tan y, and now differentiating with respect to x implicitly, we have that x is sec squared of y times dy by dx. Tan differentiating to sec squared is a pretty standard result, but if you don't like that, you can set tan equal to sine over cos and use the quotient rule. Now, sec squared of y is equal to 1 plus tan squared of y, and instead of writing tan squared of y, I'm going to write tan of y all squared. I've done that because now remember that y is equal to arctan of x, so I can replace y with arctan of x, and we'll see what happens. Tan of arctan of x must just be x, so this whole thing is just 1 plus x squared, and if we divide by that, we get that dy by dx is equal to 1 over 1 plus x squared. And oh look, it's a witch! I told you there was a reason we were doing this. So with these two lemmas, let's now put all of the pieces together and find the area under the witch. We'll integrate to calculate the area beneath the curve. Now remember, the curve has this formula, which by our first lemma is equal to this. But this actually only converges for x is less than 1. So we're actually going to find the area of this strip here between 0 and 1. So we're going to integrate between 0 and 1, and because these are equal, integrating both must yield the same result. Ready? Let's start with the infinite series, because calculus doesn't really get much easier than this. We just add 1 to each of the powers and divide by the new power. And we're going to do this between 0 and 1. Obviously, this whole thing is 0 when x equals 0, so substituting x equals 1, we get the alternating series that we've been looking for. And this must be equal to this integral up here. I think you might see where this is going, but let's do it. By our second lemma, differentiating arctan of x gives us this 1 over 1 plus x squared, so integrating 1 over 1 plus x squared will give us arctan of x. So now we evaluate this between 1 and 0. Arctan of 0 is 0, and arctan of 1 is pi divided by 4. And there we have it. By the magic of the witch, these expressions are equal. Both represent the area beneath this witch between 0 and 1. But, and it's a big but, I cannot lie, this might in some way feel unsatisfying. Why does the area under the curve have something to do with pi? Sure, the curve stems from a circle, but it isn't a circle. Well, don't go away, because I found a really intuitive explanation for why that might be the case. There is in some sense a clear relationship between the area of the circle and the area under the witch, and what's more, we can see it using an elementary, calculus-free method. First, I'm sure you're still wondering, I'm discussing a curve called the witch as if it's totally normal. Why such a sinister name? Well, indulge me in a short break in the mathematics for an etymological tangent. The curve is named after the tragically overlooked mathematician Maria Agnesi, one of the first women to be offered a mathematics professorship. The curve was studied earlier by our old friend Fermat and a guy named Guido Grandi. Agnesi wrote about the curve in her 1748 treatise on calculus, her Instituzioni analitiche, which was eventually translated into English by Cambridge professor John Colson. There are a few conflicting stories about the exact wording in these texts, and about whether which came about due to a mistranslation, so I felt I had to view these texts with my own eyes. So I've gone to my old university library where they actually have an original copy of the text, so let's see what it has to say. And now we're actually at the John Rylands library because it turns out this is where the books actually are. Stupid. They kindly let me examine a copy of Agnesi's Institutions. I was very nervous about handling a book that's over 250 years old, but an enormous thank you to the team at John Rylands Library for letting me view these works. And there it is.
Laversiera, which apparently means witch. There it is. So cool.
Here we clearly see that she uses Laversiera for the curve. And also just look at these old diagrams, how awesome are they? Then we looked at an original copy of Colson's translation where he writes that the curve is vulgarly called the witch. Lo and behold, the Witch of Agnesi. So where did the name Versiera come from, and does it actually mean witch? Well, while Guido Grandi wasn't the first to study the curve, he was the first to name it. In a 1718 treatise he writes, which I usually call Versiera, or in Latin, Versoria. Versoria meant a rope used to turn a sail, deriving from the Latin vertere, which means to turn or change, and sinus meaning sine curve, or, among other things, a bulge in a ship's sail. While Grandi says nothing for his motivation for the name, a common explanation for Grandi's name is that Versiera means turning curve, as it derives from this line turning about the origin. Now, at the same time, the Italian word avversiera meant a female adversary or the wife of the devil. This would come to mean more generally a female fiend or demon, the equivalent of witch. As we saw, Versiera persisted into Maria Agnesi's Institutions, and this work was much more prominent, considered the greatest introduction to calculus at the time. So the curve came to be named after her. John Colson's translation was published posthumously in 1801, where Versiera was translated into witch. Many writers argued that this was John Colson's mistake. Clifford Truesdell berates Colson, accusing him of mistaking Laversiera for Laversiera. However, it was common at the time to refer to Aversiera as just Versiera, through aphasis, where the initial sounds of words are omitted, kind of like how we say cos instead of because, or how lone derived from alone. We see evidence of this in Pietro Fanfani's Vocabulary of Tuscany, where he writes that because it was taboo to speak of the devil or the wife of the devil, people invented different names like Versiera. He cites several writers using Versiera in this context long before Grandi, so we can assume that Versiera was in common use. Versiera essentially became a homonym. It has two different meanings, so translating Versiera to witch might have been a mistranslation, but it wasn't totally without foundation. Others, like Stephen Stigler, claim that Grandi was aware of this double meaning and deliberately named the curve Versiera as a pun. However it happened, Versiera stuck and witch persists into English nonetheless. And as a final point, T.F. Milcrone argues that Witch of Agnesi is inappropriate as a name for the curve, as the word's evil connotations do little to honour Maria Agnesi, who lived at a time when women in maths and science struggled for acceptance. Maria Agnesi, by the way, is reported as being prodigiously intelligent, mastering 7 languages before turning 11, debating philosophy with her father's circle of academics in her late teens, all while acting as tutor to her 20 younger siblings. Yes, 20. After writing one of the era's greatest textbooks, she spent the second half of her life devoted to helping the sick and homeless, eventually founding her own home for the elderly. She donated so much that despite being born into one of the wealthiest families in Milan, she died poor at the age of 80 and was buried in a mass grave for the impoverished. My use of the term witch is just a bit of fun. It's directed to the curve, and none of its sinister connotations are directed at this remarkable person who I deeply respect. Anyway, let's get back to the mathematics and explore the area under the whole curve, because this turns out to have a surprising answer, and it reveals the relationship the witch has to the circle. To do this, we need to integrate from negative infinity to positive infinity, but by symmetry, I'm just going to integrate from 0 to infinity and double the answer at the end. We handle this by integrating from 0 to h, and then we'll let h tend to infinity. As we know, this just means evaluating arctan of x between 0 and h, which is just arctan of h, and the limit of this as h tends to infinity is pi over 2. And since we have to double the answer at the end, we get that the area is pi. Now that's pretty cool, but what's the area of that circle? Well, using pi r squared, remembering that the radius is a half, we obtain pi over 4. That means that the area under the whole witch is exactly the area of 4 of these circles. And by the way, that's true regardless of the size of circle you use to draw the witch. How awesome is that? And do you know what else has an area of 4 times this circle? A sphere of the same diameter. That's right. The area under the whole curve, defined by a circle of a given diameter, has exactly the same area as a sphere of the same diameter. I'll try to demonstrate this by starting with this sphere and plotting a big witch. Cutting it out and into pieces, we can see that the curve almost perfectly covers the sphere, I say almost, I can't actually draw an infinite curve, and the flat area cannot perfectly wrap around a curved sphere, but hopefully this gives you the idea. Now, my mind was blown by this, but all I kept thinking was, why? Why exactly do 4 of these circles fit under the curve? Is there an intuitive reason? I couldn't find one anywhere, but I did make a satisfying discovery that sort of puts things into perspective. Consider only the half witch for now, defined by this semicircle. We're going to pick 2 points and consider this band. We trace across, finding 2 points on the circle, and now consider this sector. I want to compare the area of this sector to the area of its corresponding band. And what's more, we can make this comparison entirely without calculus. We'll start by giving a different description of the curve because finding the area of a sector demands knowledge of this angle in here. So we'll redefine the witch based on the angle the ray makes with the y-axis. So call this angle in here alpha, and we want to describe the coordinates of this magic point in terms of alpha. Again, pause here if you want to work it out. The x-coordinate represents the base of this right-angled triangle with a height of 1, and this angle in here is alpha. So that means that x is tan alpha. As for the y-coordinate, draw in this line here. By Thales' theorem, an angle subtended from the diameter of the circle is a right angle. So here we have another right-angled triangle, and this time the hypotenuse is 1, which makes this opposite side sine alpha. And now we're going to project a line across, because what we actually want is this length here. This is y. And we can get y by doing 1 subtract this length. And that length is part of this right-angled triangle. And notice we can work out this angle here, which is also alpha. So what is this red length? Let's call it A. And looking at this top right-angled triangle, we have that sine alpha equals opposite over hypotenuse. So that's A over sine alpha. Multiply by sine alpha, and we get that A is equal to sine squared alpha. But y equals 1 subtract A. In other words, 1 subtract sine squared alpha. In other words, cos squared alpha. So putting it all together, we have that if the ray makes an angle of alpha with the y-axis, the magic point it defines is given by the coordinates tan alpha cos squared alpha. This is called a parametric description of the curve, as it depends on this extra parameter alpha. Now back to our 2 points that define this band. We're going to choose them to be very close together. The first will be defined by a ray of angle alpha, the second by a ray of angle alpha plus phi, where phi will be taken to be very small. My diagram is absolutely not to scale, but I'm just drawing it nice and big so you can see what's going on. We'll deal with the smallness of phi and its implications in a second, but just a reminder, we want the area of this sector and the area of this band. We'll start with the sector, and to find its area we need this angle in here. So allow me to draw yet another diagram so that we can find that. We'll use the fact that this blue line and both of those red lines are radii, so we have 2 isosceles triangles. That means that this angle here is alpha, and this angle here is also alpha plus phi. And because angles in a triangle sum to pi, we know that this one is pi subtract 2 alpha, and this one is pi subtract 2 alpha plus phi. And so that angle between the 2 red radii is this one subtract this one. We'll see that the pi's cancel, the 2 alphas will cancel, and we'll be left with just 2 phi. Now, because phi is very small, we're going to make 3 assumptions. First, we'll assume that this sector is actually basically a triangle. Then we'll assume that this band is actually basically a trapezium, or trapezoid if you're in North America. Third, we'll allow ourselves to use these well-known small angle approximations. We can use them because these functions are incredibly close to those values when we take phi to be very small. Obviously, the smaller we make phi, the smaller the errors created by each of these assumptions. Making phi arbitrarily small, then summing up all of these areas is basically what it means to do calculus. Let's continue and find the area of this sector then, which we're idealizing as a triangle. Using this formula for the area of a triangle, we have half times half times half times sine of 2 phi. Using our small angle approximation, we can say that sine 2 phi is essentially 2 phi, and we're dividing by 8, so all in all we have that this is equal to phi over 4. Now onto the trapezium, which is significantly more complicated, so let me clear away some of this board. So using the formula for the area of a trapezium, we need to take half of this perpendicular height and then times by the sum of the parallel sides. Start by thinking about this perpendicular height h. Now this comes from the fact that it's the x distance of this band. So in other words, it's going to be this x-coordinate subtract this x-coordinate, that's going to give that length here. So in other words, it's tan alpha plus phi subtract tan alpha. Now these red distances here basically just come from the y coordinates, so this will be cos squared alpha plus phi plus cos squared alpha. And I almost forgot we also need to times this by a half. Let me get rid of that trapezium now because I don't think we need it. And now we proceed with the headache of trying to simplify this damn thing. Now this is a great exercise if you're currently learning about trigonometric identities and that sort of thing, so pause now if you want to work it out for yourself. Otherwise, let's continue. Take a deep breath. We're going to start with the cos squared alpha plus phi plus cos squared alpha. Now this is equal to cos 2 alpha plus 2 phi plus 1 all over 2 plus cos 2 alpha plus 1 over 2, and that's using the fact that cos squared of theta is equal to cos 2 theta plus 1. Now we'll factor out that half, collect those ones together, and now use the double angle formula for cos. Just about fit that on, and now we'll invoke our small angle approximations, saying cos 2 phi is basically 1 and sin 2 phi is essentially 2 phi. Now we can see we've got two cos 2 alphas, two of these, so we can now re-expand that half into there to simplify things. Now, we don't like that 2 alpha. Usually, if we take the cosine or sine of something in problems like this, we want to just do it of alpha, not 2 alpha. So let's use our double angle formula. And now finally, 1 subtract sine squared alpha is another cos squared alpha. So we have 2 cos squared alphas and 2 phi sine alpha cos alphas, so we can bring the 2 out. And we're done! Although it might not look like it. You might be wondering what on earth are you doing, but it'll come clear in a second. Don't question the witch. So we can rewrite that whole expression in red with this expression down here. And now the next step is to simplify this expression in blue. Another deep breath, and let's start by replacing tan alpha plus phi with our sum of angles formula. And now we'll immediately invoke the small angle approximation to write tan phi as phi. And now we want to subtract this tan alpha. Think of it as tan alpha over 1, and now multiply numerator and denominator by 1 subtract phi tan alpha. Now there's a common denominator and we can subtract. Okay, now we can subtract these numerators, so we have tan phi here, subtract tan alpha times 1. So tan alpha, subtract tan alpha, that's going to die, so we'll be left with a phi. And then we have minus tan alpha times minus phi tan alpha, so that's positive phi tan squared alpha. And now there's a common phi up here, so let me factor that out. And now we use the identity that 1 plus tan squared alpha is sec squared alpha. But I'm actually going to write it as 1 over cos squared alpha. And then this original denominator of 1 minus phi tan alpha, I'm going to rewrite that tan alpha as sine alpha over cos alpha. Why are we doing that? Because tan is the worst, always get rid of it. Now let's just simplify this whole thing. The numerator will be phi and the denominator will be cos squared alpha subtract phi sine alpha cos alpha. And we're done. So let's replace that blue expression up there with this yellow expression here, and we'll watch some fireworks. So as grueling as this whole process has been, look what happens now. The half cancels with the 2. But that's not all. The cos squared alpha minus phi sine alpha cos alpha cancels as well. And is there anything left? Yes, there is a phi. So after all of that, the area of this idealized band is just phi, and that is 4 times the area of this idealized sector, because we said that that was phi over 4. Oh, it's so good! And that'll be true regardless of the 2 points we choose, as long as we choose them to be very close together. So if we split the whole curve up into bands, thereby splitting the whole circle up into sectors, each band will have area of 4 times its corresponding sector. Therefore the area of this whole half witch is 4 times the area of this semicircle, and therefore the area of the whole witch is the area of 4 of those circles. Oh, I just love it. This reveals a fundamental connection between the area of the curve and the area of this circle, which is why pi pops up in the area under the witch. Because the formula for the witch can be represented as this infinite series, pi sneaks in as a result of this infinite series. So, to conclude, while there might not be a good reason for the name witch, the curve certainly hides a lot of mathematical magic. Thank you kindly for the view. I'm glad you watched all the way through. To my patrons, as always, the biggest thank you. Please consider supporting me too. If not, don't worry, but do be so kind. Before you leave, be sure to subscribe. I hope our study of the witch for now did scratch your mathematical itch. This has been another proof, as always, under another roof.